When electricity flows through a wire, it's chaotic. Millions of electrons bounce and drift, making it difficult to measure the exact resistance of a material while the current is actively rushing through it. To get the most precise measurement possible, we have to force the current to a complete standstill. We do this to solve a specific problem, determining the exact value of an unknown resistor. By arranging our electrical components into a specific geometric shape, we can create a balanced system that reveals the unknown value without relying on a direct, messy current reading. This schematic shows the architecture we use. It is a four-sided diamond network made up of four distinct resistors: R1, R2, R3, and our unknown R4. To drive the circuit, we need a power source, B and D, with a galvanometer. A galvanometer is a highly sensitive electrical instrument used to detect and measure tiny amounts of current. This new path forms the galvanometer arm. This cross-linked geometry isn't arbitrary. It creates a literal bridge between two parallel electrical paths, setting up a physical comparison that we can manipulate. When we apply power to this circuit, the main current hits junction A and splits into two paths, I1 and I2. Because the potentials at D and D aren't equal yet, a messy crossflow of current, labeled IG, leaks right through the galvanometer in the middle. But here is where we take control. By adjusting the values of the known resistors, we change the voltage drops along the two parallel paths. We tweak them until the potentials at vertices B and D are exactly identical. When that happens, the central current disappears completely. We verify this using the galvanometer. We are looking for null deflection. Null deflection occurs when the needle of a meter rests exactly at zero, physically confirming that absolutely no current is flowing through that central arm. This changes the math. We apply Kirchhoff's junction rule. Total current entering a junction must equal the current leaving it. Since zero current is flowing down the center, all the current entering vertex D from R1 has nowhere to go but straight through to R3. I1 now perfectly equals I3. The same logic applies to vertex B. Every single electron making up current I2 flows seamlessly across the junction and becomes I4. By forcing the central current to zero, we remove the cross-contamination. The complex, leaky network is now just two independent, predictable streams of current. To find our unknown resistor, we need to map the voltage. For this, we use Kirchhoff's loop rule, a principle stating that the algebraic sum of electrical potential differences around any closed circuit loop must equal zero. Let's look at the top half of our diamond. In our perfectly balanced state, the potential difference across R1 is perfectly countered by the potential difference across R2. Mathematically, negative I1 times R1 plus I2 times R2 equals zero. We can quickly rearrange this to show that the ratio of the currents, I1 over I2, equals R2 over R1. Now we apply that exact same logic to the closed loop on the other side of the bridge, passing through R4 and R3. The voltage drops here must also cancel each other out. I2 times R4 minus I1 times R3 equals zero. Simplified, this tells us that the current ratio, I1 over I2, is also defined by the ratio of R4 to R3. We now have two separate equations that both equal the exact same ratio of currents. Because they share that value, we can drop the currents entirely and set the two resistance ratios equal to each other. When the bridge is perfectly silent, the physical resistances are mathematically locked together. In a real-world laboratory, we assign specific jobs to these components. R1 and R2 are fixed known values. R3 is our variable resistor. We know its value, but we can actively change it. That leaves R4 as the mysterious unknown we are trying to measure. To find the value of R4, we manually tune the variable resistor. We keep adjusting the resistance of R3, carefully watching the galvanometer until the needle finally settles precisely on zero. You turn the brass dial carefully. The resistance changes until the needle snaps straight up, locking into that perfect zero. At that exact moment of balance, the math does the work for us. The value of our unknown R4 is simply the value of our variable resistor, multiplied by the ratio of the two fixed arms. This is a historical resistance box, an instrument containing multiple coiled wires of known resistance that can be switched in or out of a circuit. Tools like this allowed engineers to tune R3 with incredible precision. By understanding the mathematical rules of the circuit, we no longer need to rely on measuring a moving current. Instead, we use the complete absence of flow to determine the exact resistance of any component.